start. The first concentration that we're going to discuss in chapter 13 is that of a mass percentage, where you take the mass of some solute in solution, so A is the solute, you divide it by the total mass of the solution, you multiply by 100%. This is one of the more effective ways of describing concentrations if you're dealing primarily in balance work, but this is not the most efficient way, in my opinion. The most efficient way to express a concentration in bench chemistry for us is probably going to be molarity, and we will talk in depth about molarity. And this is the first of several. Okay, from this one we can talk about parts per million and parts per billion. One is going to be the mass of something over the total mass of solution times 10 to the 6th, which gives us a concentration that can be expressed as X parts per million, or ppm. Parts per billion is also going to be the times 10 to the 9th, so same formula times 10 to the 9th. Now, this is for really, really small amounts in solutions, right? Whatever your total mass of your solute is going to be a really small number compared to the total mass of the solution, which is why we have to multiply it by either a billion or a million to express the concentration.
Is this PowerPoint on campus?
Not right now. Like, it's not available to you right now. It will be. Was that what you were trying to ask me earlier? Okay, sorry. I completely forgot that. Yes, ma'am?
What's the number for parts per billion?
10 to the 9th.
Sorry.
Okay. I'm going to turn off the other light. Just don't fall asleep on me in the dark, warm room. Huh? It's the winter. We leave the heater on every night. Gotta love it. All right, another way that we can express a concentration is going to be with mole fractions, where we take the moles of our solute and divide by the total moles of everything in the solution. So that includes the solvent and the solute. In particular, mole fractions are nice because you can express the mole fraction of the solvent as well as the mole fraction of the solute. So this is not like a solute dependent concentration. All right, so those are some of the more obscure methods for expressing concentrations. Every situation has its own reason why you should use that particular concentration. Sometimes you're not given the information you need to calculate a molarity, but you have seen molarity before. We covered it in the very beginning of last semester. And molarity is calculated using moles of your particular solute, dividing it by the volume in liters of whatever your solution's volume is going to be. And that includes when you add the solute. So that volume underneath this equation can be impacted by the amount of solute that you add. Okay? For the most part, when we talk about molarities, we're talking about very precisely measured concentrations. We have very specific glassware that helps us identify a solution as precisely made. And so that is a lot of what you see whenever we do labs this semester. You'll see some of my fancy volumetric flasks. Those are designed to deliver specific volumes and very correct volumes, if you will. Okay? This particular concentration is temperature dependent. As temperature changes, the density of a fluid changes. And since we're talking about a volume of a fluid, the volume can change with temperature, right? So molarity is going to be the one of our concentrations that is temperature dependent. Another concentration is going to be molality, and this is one I think I asked you about yesterday for your daily Q. Molality is a useful version of molarity because it does not use volume, it uses a mass. So instead of taking moles and dividing it by volume, we take moles and we divide it by kilograms, and we get rid of that temperature dependence. If I had to choose a concentration you would likely see in any advanced chemistry textbook telling you how to prepare things, I would guess molarity first and then percent by mass second. So that first one we talked about. Molality is used in more organic applications, so more like organic type labs, because that is where they typically mess with temperatures when they're doing their experiments. So, okay. When we're trying to convert molarity and molality, just kind of keep in mind that you know how to do unit analysis and unit conversions. So if we're talking about a concentration in moles per liter that we're trying to convert to moles per kilogram, what we need in between is going to be a density. And so in some of the problems that we practice, you're going to see that you're given densities of solutions for a reason. We're trying to get this to moles per kilogram. To get from one to the other, got to use a density in between. And remember that most densities are given in grams per milliliter. So what's another part of this that we're going to have to use? It's another step we'll have to do. Grams to kilograms, right? We actually want to keep the moles. So let's start with something that's 1 mole per liter. Let's say that our solution's density is 3.2 grams per milliliter. Can I just do that? Heck no. What's wrong? Grams needs to be in kilograms. What else is a problem? Hopefully you recognize that these milliliters and liters do not match. So we want to go 1 milliliter or 1,000 milliliters. Cancel these out. Those out. Now we've got moles and kilograms. Do we want, or I'm sorry, moles and grams. What do we want? We want kilograms, so we're going to do, okay. So we can convert a molarity to a molality by doing these steps. Will that always be the same steps? Yes. Okay, so it's a good idea to write it down. Will we always have to multiply the grams to get them into kilograms? We always have to change milliliters to liters? Yes. A lot of times our simple unit for density is just grams per milliliter. I'm going to show you. This is the thing that they're looking at right I can. Just give me 1 second.
No, you're good. I can keep going.
As long as we can kind of see the board. Okay. We got 2 topics left in chapter 13 that are not concentration based. One is going to be on colligative properties and the other is on what we call a colloid in a solution. Okay? The first is going to be the colligative property that we're going to study in lab the rest of the week. And that's going to be referred to, the one that we're going to specifically focus on is the freezing point depression. Colligative properties are going to depend on solute particles present in number, not identity. So the amount of the solute I put in my solution is the thing we're going to study, and we're going to call that a colligative property. There are quite a few colligative properties. There's a few listed. One that we're going to study is freezing point depression. I promise we're going to come back to this. Is anybody still writing this down? Cool. There are several colligative properties we could study. In lab, we're going to focus on a freezing point. And freezing point depression. So what does the term depression mean in that sentence? Or in that term? Lowering. Okay? So we're going to be studying freezing point lowering. This is one of my favorite labs because we get to use dry ice. You guys have seen the dry ice lab before? Or you've seen the dry ice. You haven't seen the lab. Same idea. No, we're going to go the other way. In order to understand a colligative property, we have to talk about vapor pressure. Again, we've talked about vapor pressure before, especially when we discussed liquids and intermolecular forces and gases. And vapor pressure, if you'll remember, is the pressure involved above a liquid, immediately above a liquid. One of the things to remind you of is that depending on the concentration of a solution, if you have a lot of the solute present in a solvent, you may have stronger intermolecular interactions, right? The more solute you add, think stronger intermolecular interactions, which means lower vapor pressure because less is escaping from that solution. So when we talk vapor pressure, think vapor particles above the liquid. And when we talk vapor pressure, lowering because we're having less of those particles escape when we add a solute. The more solute we add, the less of the particles that are going to be able to escape. So one of our colligative properties was vapor pressure lowering. The more solute we add, the lower the vapor pressure goes. And it's because primarily of those higher intermolecular attractions. The more solute there is, the more ability those solutes have to interact with their surroundings, meaning intermolecular attractions. Okay? The vapor pressure of any solution will always be lower than that of its pure solvent. So Think the difference in vapor pressure between pure water and salt water. One of those two things is always going to have a lower vapor pressure because of the solute particles. It's the salt water.
It's lower than the pressure.
Correct. Okay. In order to actually calculate vapor pressure, we introduce Raoult's law. Raoult's law says that the normal vapor pressure of something, that P naught A, so that far right term, this is all one term, okay? It's going to be your normal vapor pressure at that whatever temperature your solution is being held at. The mole fraction of compound A is going to be XA. So this term, and we talked about mole fractions just recently, all of that together is going to be able to calculate the pressure of your solution, the vapor pressure of your solution. In this particular case, the mole fraction you should be using is the mole fraction of the solvent, not the solute. So if we're studying a solution that has, say, a salt and some water, okay, salt dissolved in water, water is the solvent in that case. In this particular case, if we wanted to know the vapor pressure of that solution, we would need the mole fraction of the water to multiply by the normal vapor pressure of that water. Yeah? Yeah, that's like the solution vapor pressure, correct. So this is the solution vapor pressure for all, and this takes into account the water's mole fraction. And this is going to be the normal vapor pressure of the water at whatever temperature it's at. So this is like pure solvent. This is the impure solvent that we're trying to calculate. Okay? Yeah?
Is it a solvent or a solid, did you say?
Solvent. Raoult's law deals in the solvent. Okay. From there we talk about boiling point, elevation, freezing point, depression. So solute presence can elevate a boiling point. Up here, we see a lovely phase diagram. Seen them before. On our phase diagram, we can see that the shifted version of this phase diagram, aka where we added a solute, is going to be these blue lines. These blue lines at 1 atmosphere, remember, your boiling point is going to be increased, okay? Your freezing point is decreased. So adding a solute lowers our boiling points. Increases our boiling points, lowers our freezing points. Boiling point, elevation, freezing point, depression. And it's because of the shift in the phase diagram, specifically. Which is, of course, always related to the pressure above the solution. This is why we pour salt on our roads, guys. Lowers the freezing point of the water. Okay. When it comes to calculating the change in the boiling point or the change in the freezing point, we need to know the constant associated with the specific solvent that we're working with. So Kb is a constant, and this lowercase m is the molality of the solution you're dealing with. We multiply a constant for the solution that we're looking at, or the solvent that we're working with, times the molality of the solution, and we get the change in the boiling point or the change in the freezing point. So we'll look at both equations, but they're the same. So Kb is the boiling point elevation constant related to the solvent. So in other words, if we're talking about water, water is a solvent, we would use the Kb for water. We'll also see Kf, which is just going to be the freezing point constant for whatever solvent. Yes? This would be the change in the boiling point from its normal boiling point. Good question. And yes, since these are constants, you'd have to get them from tables, and you can see one that we've got in your book. Yep. The lowercase m is molality. The uppercase m is molarity. I'm sure that totally clears it up. Capital M's versus lowercase m's. The lowercase m, when you see it typed, is also usually italicized. The capital M is not. The other way to express these instead of using the shorthand is to write moles per kilogram and moles per liter. If you want to avoid the which one is this argument altogether, use those instead. Okay? Like I said, the change in the freezing point can be calculated the same way, just using the freezing point constant and the molality. Please note down here at the bottom, it does say delta TF is subtracted from the normal boiling point, whereas delta TB is added to the normal boiling point because we're talking boiling point elevation, so increase, and freezing point depression, so decrease. Kf is also a constant, yes. So there's this table in your book that gives you those different K values depending on if you're talking about a boiling or a freezing point, yes. Yes, related to the solvent. So over here you can see an example. We've got the boiling point elevation and freezing point depression constants, and they're listed by solvent. So water, benzene, ethanol, etc. Carbon tetrachloride. Okay, so in both cases, just remember, it doesn't matter what the solute is. How much solute is present is already going to be taken into account when you calculate a molality, but it does not matter what the solute is. Doesn't matter if you're dealing with a salt solution, doesn't matter if you're dealing with a sugar solution, doesn't matter if there's something in there that you've never seen before. What matters is the solvent and how much of that solvent is present. We care about how much is there, right? But we don't care what the solute is. Okay. From there, a few more colligative properties that we want to talk about. Just, again, the term meaning the effect on a solution. For this particular conversation, we want to talk about what happens when we add things that dissolve in solution, and when they dissolve, they dissociate into ions, right? So think salts. Something like sodium chloride is going to dissolve into its individual positive and negatives. Because there are multiple particles that get dissolved, we see that the effect of that is actually going to be greater than those of non-electrolytes. So if we compare a salt solution to a sugar solution, we're going to see that a salt solution is going to have a greater effect on, say, the freezing point than something like a sugar would, or something that doesn't dissociate into ions. Okay? Just making the argument that if we have something that dissociates into many parts, the effect is going to be amplified versus something that doesn't dissolve into many parts, just kind of stays the way it is and gets surrounded by water particles or whatever particles you're dealing with. Woo. Okay. When it comes down to it, it is not a like, hey, since NaCl dissolves into 2 particles, that it should be double the effect. It's not like that, but there is a change, right? It is an amplified effect. We're not saying that since there's going to be twice the particles for one solute, that it means that the effect should be doubled, right? It's not like a directly proportional situation. Okay, from here we have to talk about the Van't Hoff factor. Anybody remember what the Van't Hoff factor is from when you were reading? Chapter 13? Of course we don't. So, one of the things to note about, One of the things to note about salts is that when they dissolve, they don't necessarily always completely dissolve. Okay, so dissociation is something we kind of take for granted, and we just assume that something like NaCl will completely dissolve every single one of its particles into Na ions and Cl minus ions. Okay, we take that for granted. That is not the whole picture. The whole picture says that in reality, some of these Na particles might still be attached to their chlorine particles, and that they are not going to necessarily have what we call 100% dissociation. And we will talk a lot more about 100% dissociation versus weak dissociation when we get to our acids chapters. But for now, one thing to kind of understand is that at the particle level, things are not cut and dry, right? We're not just going to dump a bunch of salt and water and all of it's going to dissolve and all of it's going to dissociate into its 2 different parts. That's not the reality of the situation here. Everyone? Okay. What is going to happen over the course of a solution's life, especially if there's some kind of movement going on, aka you're stirring it or it's being stirred, it's agitated, etc. The reality is that sodium and chlorine particles are going to come together, move apart, come together, move apart, come together, move apart constantly, okay? And the way that we can, and this is going to, obviously this is going to have an impact on our concentration. We're going to assume that everything dissolves, and we're going to express a molarity as such. However, that molarity is not 100% accurate. Let's put it that way. So we have a way of trying to correct for that. And that's the Van't Hoff factor. I want to move on, but I'm afraid to because I got yelled at last time. All right, so the Van't Hoff factor is something that we use to take into account this idea that when we dissolve our particles, not all of them are actually going to be by themselves. So for something like NaCl, when NaCl dissolves, what should happen is we should get double the number of particles in solution, right? Because Na goes off by itself, chlorine goes off by itself. Well, in reality, the lower the concentration, the more likely it is to have gotten to specifically double, okay? The higher the concentration, the less likely it is to have doubled. Now, the math is a little complicated, so we're not going to look at it. What we're going to do is we're going to take for granted, or we're going to just take this at face value. The higher your concentration in an electrolyte solution, the less likely it is to completely dissociate. Okay, that's our assumption that we're going to make. The higher the concentration of your solution, the less likely it is to completely dissociate. And we can analyze this using a bunch of different salts, right? Not just sodium chloride, which is our simple one that should dissolve into 2. We can look at K2SO4, which should, in theory, dissolve into the SO4 polyatomic and 2 different potassium ions. So there should be 3 parts. As we get lower and lower, we see we get closer to 3 parts. But the higher the concentration, the less complete dissociation is. Yes? So the higher the concentration of your electrolyte solution, the less likely it is to completely dissociate. is also a good summary. The number of particles present is concentration dependent. Okay, this is like a good summary sentence for the Van Hoff factor. This is your daily reminder to wash your hands, use a hand sanitizer, try not to touch your face, do what I say, don't do what I do. Right? I touch my face all the time. Be aware. If there's anything that Corona has taught you, it must be how many times a day you touch your face. I feel like you are probably more bodily aware of how often you touch your face now than you ever were before.
I know it's a more disturbing thing some people do.
Yeah. Wow. Like how many
Like
people
lick those
didn't
fingers
wash
and
their
stuff
hands?
like that. Like that.
My favorite is we were at Thanksgiving and my mom has gotten her vaccine and whatever. There were like four of us or whatever. And my husband, who I love dearly, he didn't have his mask on and he just like coughs into the middle of the table. We're like playing a board game. And literally like my dad just kind of looks at him as like and I turn to him and I'm like, his mask was like down here too. Like his mask was on his face. He like, and literally oh my God, I still give him crap for that. It's been 3 months. It's been like 2 months. I'm still giving my husband crap for that. That is horrible.
Did you ever think about how gross bowling is when you all
Or,
play
like-
in the same ball and then you're eating food at the same time with other stuff?
Yeah, I mean, we are a society that has lived as long as we have, and who knows why, right? Like, you mean like a bowl of candy? Are you talking about like grabbing things that we used to
You all
do
three
that
of
we
you have the same
shouldn't?
ball and then you eat out of the same container.
I think the movie theater is worse. It's so gross.
Oh yeah, the movie. I can't believe I used to go to the movies. Like, ew. They're all sitting in the same gross seat.
Oh, they were like, okay, I went when they reopened, and they were like insanely clean. They were like bringing the wand around, and they wiped everything down with a wipe. It was intense. They were like, you have to wear your mask when you're in the movie theater. It was the cleanest place I've been during Corona,
Okay, but
hands down. Okay, before that, absolutely.
It's like on the floor.
All right, okay. All right, so real quick, we're almost done with this, I promise. We can modify our change in freezing point and boiling points by adding in the Van Hoff factor. So it's just another constant that we have to insert. It's labeled I, and it just gets added to this equation. Human beings are disgusting. That's the end of this conversation. It is what it is. We live in the time of Corona. Several doctors that I've talked to are like, you're going to be in a mask until the end of this year. Like 2021. I was like, no.
2021 to 2020.
This is, I think once May hits, I'm just not going to leave my house anymore. It's fine. 6 months.
Yeah, there's a show, but it's outside. So it's like when they have all these ones that are like in an auditorium, like, oh yeah, this year like you had to do it outside.
It's like 2021.
It's like
Just like,
to go to a conference this summer.
I would like someone to just tell me, like, we could just skip to 2022. That's fine.
2021 is 2021.
I don't know what I'm gonna miss in 2021 that I couldn't just skip, sleep through, etc. No idea. I'm sorry. Okay, yes, I is a constant. Good question. Okay, so we have a couple of other things we need to talk about, specifically semi-permeable membranes and how those are affected by solute and solution concentrations. Osmosis, you guys have all learned about. You've heard the word osmosis before. Let's go with that. A lot of times what we're seeing when it comes to semi-permeable membranes, like your cells or the membrane around your nucleus in your cells, things of that nature. With those semipermeable membranes, they'll really only allow certain substances through if they're at specific concentrations. This is where we can also kind of discuss diffusion, where we move from something that has a high concentration to a low concentration, whatever that concentration might be, right? So something that has a high concentration of water may want to move that high concentration of water towards an area of low concentration of water. So this term concentration and this movement of particles is going to be dependent on the amount of solute present in your solutions. Okay, and you probably don't really remember from biology, but you talked about when cells swell, when cells shrink, and when they're in their natural environments and they're happy. When they swell, they can pop, right? You remember that? Apoptosis is the term. When they shrink, they crenate. Crenation is the term. And when they're at that equilibrium, anybody remember?
We didn't learn the swelling and shrinking. We learned equilibrium.
Okay.
No, I remember. Like, we had like a diagram of
Yeah,
it.
you had to have learned just because. So apoptosis is important because it's what causes your cells to like go away, basically. Yeah. You probably did labs on this, and you did some other cool stuff. Really, what I want to get across is that osmosis is the movement, right? The movement of solvent. So think water, from a high solvent concentration to low solvent concentration. Whenever it comes to anything in this class, we move from high to low. Okay, so large amount of heat to small amount of heat. Sure. So high solvent concentration to low solvent concentration. The movement of solvent particles from high concentration to lower. Not solute, solvent. The difference between osmosis and diffusion, because I guarantee you don't remember that, is that with osmosis we talk about water movement, with diffusion we talk about solute movement. See, there are some things I like teaching in biology. There's a lot more things I don't like teaching in biology. Like, you can only teach Punnett squares for so long before you have to move on to a topic nobody wants to learn.
Stories were funny though.
Like species predation.
Some of the stories that they gave for the Punnett stories were kind
Yeah,
of
that stupid hybrid I'm about the dinosaur.
You know, back in the day, they used to let you, like, blood type your own, like, yourself in labs. Like, they used to let kids do that. 70s, 80s.
But that would require drawing blood this time.
Right, like, now it's, like, super taboo. You can't be anywhere near someone's blood, and if you are, you have to file, like, 20 pages of paper. Yeah. All right. Here's an equation for calculating the osmotic pressure of a solution. Do you need to know this equation? No. Am I going to ask you to do math with it? I don't think so. So I would not worry too much about this, but understand that you can calculate the osmotic pressure of a solution using the molarity. Remember, capital M is molarity. Every other term on here should look familiar. This pi is kind of interesting, right? Every other term on here should look familiar to you. Oh, there it is. Haha. When you have equal numbers of solute, it's isotonic. That's the term. The one I never remember. I like the swelling one and the shrinking ones. It's more interesting when things crenate. Do you remember learning about crenated cells and diseases?
Like sickle
Anybody
cell
remember?
disease?
Sickle cell disease is
Oh,
the one that
yeah.
has crenated cells.
It also protects you against malaria.
You remember the cancer?
Not a good trade-off. Not gonna lie.
It isn't. I'm just saying. Yeah.
I remember that.
Not a good trade-off, but that is true. You are correct. I'm just saying. Good stuff. Okay.
I did something.
Oh, look at that. We're going to talk about this. So, in blood cells, if the solute concentration outside, solute, remember they're talking about solute, but we're going to talk about osmosis in terms of solvent. So if the solute concentration outside is high and the inside the cell is low, Okay, that means low concentration of solute inside the cell means there's more water inside the cell, less water outside the cell. So which way is the water going to move? Out. Okay, so high water concentration inside, low water concentration outside means the water is going to move out, the cell's going to shrink, and we call this crenation. So that's the first situation. All right, the next situation is going to be the opposite, where we have high concentration inside the cell of the solute, low concentration outside the cell of the solute, which means the water is going to move from the low concentration of solute to the high concentration of the solute. So inside the cell, and it's going to swell. It's our opposite situation. Osmosis can get kind of confusing because it really depends on the text that you're exposed to. Some textbooks will talk about osmosis as solute concentration movement, and some will talk about it as solvent concentration movement. In the end of the day, the definition of osmosis relates to the movement of water, not the movement of solute. However, the concentration of solute is much easier to determine than the concentration of water might be. That's why we talk in terms of the concentration of the solute. Okay? All right, so here's the hypotonic solution, where water moves inside the cell. When this happens, the very famous term is hemolysis, meaning exploding. Means the blood cell explodes, because lysis means break. Hemo is cell, red cell, blood cell. Not a great situation to have to deal with. Once the cell explodes, you can't really get it back. You have to grow new ones. So if you're ever in the hospital and they take blood work and they're like worried about your pH balance or something of that nature, or they're worried about your fluids, it's because they're worried about a situation happening that will take you a very long time for recovery. Dehydration is really common. So if you're dehydrated, it means your cells aren't getting enough water and they're shrinking. And when you get dehydrated, you tend to faint, right? Those of you that have ever fainted because you're dehydrated, it's because your red cells are not getting enough oxygen, and it's because they're smaller than they should be. When they're too small, they can't carry as much oxygen, and they're not carrying it as efficiently to the parts of the body that need it, including your head. Yes? Anemia is a deficiency in iron, and iron is the thing that binds oxygen. So it's a little different, but you do feel like lightheaded and dizzy a lot when you're anemic. We're going to finish this before you take a break. All right. Last thing we have to talk about is the suspension of particles within a liquid, referred to as colloids. We've seen the term colloids or colloidal suspension before, and nothing has really changed. The difference is that when we call something a colloid, it can contain more than just what we've determined it to be before. Before we talked about it as being like crystal-based. Colloids can be anything from like fat particles to aggregated particles. You'll talk about like aggregates in this particular section. The colloid type is an aggregate type, if you will. Aggregate just means clump. Right? Clump of something. Colloidal suspensions are interesting to study because they scatter light in these unpredictable ways. We refer to that scattering as the Tyndall effect. This scattering of the light particles all is something that you can attribute to like why the sunsets look really cool, because it scatters light in these odd different ways. And when we scatter light, we change the angle that they enter our atmosphere, and the particles they move through, like the water particles that light moves through, causes that light to scatter and change. Like we see cool different wavelengths. That's why your sunsets look all these different colors instead of just one. Nature is beauty. Okay. Questions so far? Okay, we have hydrophilic and hydrophobic terms. So the term hydrophilic means what? What does hydrophobic mean? Water hating. Okay. A lot of times when we get into like more macromolecules, so biological molecules in general, we talk hydrophobic portion, hydrophilic portion of a molecule. A lot of our molecules that are biological in nature have both types or have both parts within them. Your proteins have hydrophobic and hydrophilic parts. It's why they interact the ways they do in the very specific ways they do in your body. Okay? Fat particles have a hydrophobic, hydrophilic part. The membranes that make up your cells have a hydrophobic, hydrophilic part. All makes sense because you want water inside, you want water outside, but you do want a barrier between the two. Okay? Hydrophilic, hydrophobic. I think that's it. Yeah. So, if you've ever wondered why your Dawn dish soap works as well as it does, it's because that dish soap has a hydrophobic head and a hydrophilic tail. Hydrophobic head meaning part that will be okay with water. Hydrophilic tail meaning the long part that is more non-polar, doesn't want to interact with water. Okay? We can boil hydrophilic and hydrophobic down into non-polar and polar. Polar objects are going to like water, hence the term hydrophilic, and the non-polar part is going to hate water, hence the term hydrophobic. Okay. That's all. Why don't you go ahead and take a break? When you come back, we're going to continue.
What are we doing now?
We're going to work on some practice problems. Yes?
Am I able to finish my tower during robotics?
Yeah. Yeah. They're going to be working on like reading the next thing and finishing up some questions over Unit 1. Trying to move us into Unit 2. I think by the end of the week we'll be building. So that'll be fun.
Oh, yeah, I guess it's right.
Well,
Did that really catch your brain?
I think we're both through.
Oh my god. Did you talk to her about that? Yeah. What'd she say?
Really? How we doing? I'm back. I'm
Sorry.
and so and I think my background kids therefore went and I don't remember that class.
English 1, 2, and 3?
No, 1 and 2.
Oh, you have 2 colors.
Okay, this is my water.
Did you?
This is my coffee.
It's online.
How did you make it until 7:30? Let's do it together.
Once a week, I think.
Oh, come on. That's why I'm not going to be talking about it, because I can't make it. I would get up that long.
Ask sister.
When I walked down the stairs with my eyes, is it as
Lovely.
Okay. And my son is
I don't know if you do it online.
Yeah, me too.
Okay, so I'm trying to get in my car.
Sometimes I get
And
at like 4 o'clock
the
and
car so
Because
that
like
I
that
can
one, and I figured I know people
And
who
I'm trying to get in my car.
No,
My brother
no,
started
no.
backing up and almost hit me this morning.
What?
See,
You
there's
guys drive
one,
separately
here
to
it is.
school?
Yeah, because I have to go to work and then he has to go to
Where does he have to
You
go?
can take it.
And why does he have a
There's a,
brain
we
card
can
that he
take
never
one and
drives?
open one starting
his truck. His truck
March
March.
15th.
Now, and it's
No,
done?
it works.
It's done.
It takes so much gas.
May 7th.
Oh my gosh.
You wanna do
He
that?
drives around like he's woke, like
It's-
going somewhere.
There's 21
My mom got up this morning. My mom got up this morning. She was literally gonna be like, I don't have gas to warm up my car. I'm like,
Yeah,
do we
and,
have to go on Zoom? Why did you let get that low? Like that'd be so much better than
Also,
Zoom.
yeah.
Mine's usually
Right? And
like,
if it,
and then I'm
transfers
like,
over.
Yeah, it's
it's
online.
fine.
do remote
It's
surgery.
like,
Okay,
I
it's
got,
virtual.
I got a half mile left in this
It's
tank.
not locking.
I have to get to the gas station.
I was looking
I
at
have
my mom's house.
kind of the electronics.
I'll
I'll
fix
fix
it.
it. I got
For future reference, remote start doesn't actually work.
It's
on
not
the
good.
top of it though.
My parents have gotten to zero before and like,
Do what it's supposed to do.
I know, I
there's probably no liquid
Right,
left
I'm
in
talking
the
about,
tank.
this is English
It's,
one.
we still got
Oh.
This is
this.
what sister
I
Maria
have
said.
zero
They're
sympathy
more
for
than
anybody
welcome
that
to
has that.
English Pass 1 and 2 and
I don't really
qualify. It costs extra about
You don't have to put gas in your car.
Okay, so
That's
What?
different.
I can, but then some are weird.
All right, boys and girls, you can go ahead and get started on the problem on the board. There's 2 of them. You can follow along on Canvas as well. We're working on the practice example problems. If you're having trouble reading it, I highly recommend